All right, so Rayleigh flow.
I'm gonna keep the TS diagram so I can erase the boundary layer now. So for Rayleigh flow, we have still a pipe with a constant diameter. But now we assume it's the diameter compared to the length is big enough so that we don't care about friction effects.
Okay.
And boundary layer and viscous effect. So for Rayleigh flow, we deal with heat. So that's a pipe like that, in which we bring some heat here. So we heat the pipe, we heat the flow. So it's not adiabatic anymore, but that's reversible because we don't consider any friction. So there is nothing irreversible. That's reversible. I mean, you can just stop to heat your pipe after, and you would have heat out. Then your pipe would release the heat. So that's reversible. So there is no S-gen. But since we bring some heat in, we have some Q in. As a consequence, again, delta S is going to be positive.
Okay.
Because of the heating. So that's the common point with the final flow. Delta S is positive too. Okay?
Okay.
So what's going to happen then? In the homework, that's again a subsonic case. You start subsonic here at Mach 0.5. So a Rayleigh line looks like that. So again, we combine the positive, the subsonic and supersonic case, and it goes like that. At the far right, sorry, this is the maximum conditions. You will have T star here when Mach equals 1. And above is the subsonic case. Under is supersonic case. So the difference also is that since it's not adiabatic because we bring some heat in, the total temperature is increasing. So for instance, in the homework, if we start here at 1, so with T1 and we go up to T2 somewhere here, actually we would have somewhere here TT1 and somewhere here, so when I draw the isobars. So here I have PD1, here I have PD2, and here I have T2, TT1, TT2.
Okay.
So TT is increasing, and it goes up to somewhere here. So here you have PT star and TT star here. So you can see that the total temperature is always increasing because of the heat.
Okay.
Okay.
Total temperature is increasing, and
So the Mach number
and the
increases
pressure
too.
is increasing too. Total pressure.
Yes, because of this.
Okay.
creation of entropy.
And so entropy affects pressure always,
Mm-hmm.
and temperature only if it's the heat case.
Yep.
Okay.
So that's the difference with a fan of flow. Here the total temperature increases. And so when you go to the right like that, so here you would have P1 and here P2. So you go like that, you heat when you go to the right. When you go to the left, because it's reversible, so you can imagine going to the left, you cool down.
Okay.
And that's it. So to use that in the homework, first you have to use the time rate first law that says dE over dt. The time rate second law, sorry. Yeah. No, sorry, I was right. Time rate first law, yeah, sorry. That says, so that's gonna be Q in plus work in plus, that's single in, single out, so I remove the sum, H T in plus G Z in minus Q out plus. So that's dots here because that's time rate things. Plus M dot out HT plus GZ out. Okay? You remember that?
Yes.
So here you can combine H plus V squared over 2 by HT directly.
Okay.
So you only have HT plus GZ. So here there is no work because there is no, it's not a compressor, it's not a turbine, there is no moving part, no mechanical part, so there is not either power used or power produced, so nothing here. There is no Q out because we only bring some heat in, so there is only Q in. Single in, single out, so M dot in equals M dot out. And since that's vertical, we don't go up or down. We don't consider any altitude elevation change, so we can neglect the potential energy effect.
Okay.
And that's steady state. So left hand side, the dE over dt is 0. So then, what we have is 0 equals Q dot in plus M dot times HT in minus HT out. Okay? This
HT is changing because
because the TT is changing, yeah. This can be then written Q dot in equals M dot times HT out. So I'm gonna write HT2 because 1D flow can replace all that goes in by 1 because that's constant on this one plane. And same for 2, so HT2 minus HT1.
Why if H is different, why don't we put a subscript on H2?
What's that?
If H is different,
Uh-huh.
why don't we put a subscript for H?
There is 2, 1.
Oh, the T is a subscript?
Yeah.
HT, sorry. Oh,
That's total enthalpy.
yeah, I was multiplying H times T. Okay.
No.
Okay.
That's total enthalpy that comes from here, HT, because that's H plus V squared over 2.
Okay.
I wrote that HT directly. Then from here, I'm going here, you can divide by m dot, so you would have q in dot divided by m dot equals ht. So I can replace ht2 minus ht1 by cp tt2 minus tt1. So here I would have cp td2 minus td1. Okay.
Yes.
So I went here and then I went here. And here the dots are cancelled, the time units are cancelled, and when you divide big Q by m, you have small q, the specific heat, and the dot disappear. So finally you have Q in equals Cp Tt2 minus Tt1. That's how you start the homework to that, because everything is given here besides Tt2, so you can solve that for Tt2. Tt1 is given, Q is given,
So
Cp is given.
So you want to solve TT2 using the
Yep.
chart for the Rayleigh flow.
No, you solve because you have everything.
Oh, so you can't, there's no Rayleigh flow chart?
Yes, but after. First you do that.
Okay.
And you solve for Tt2 because Tt1 is given. So here what they give is M1, PT1, TT1, and Qin. So we have PD1, TD1, M1, and Qin. And you want to find M2, TT2, PT2.
Oh, okay.
CP is given too.
So in this case, there's no way to go directly from M1 to M2 without using the static parameters or the total parameters.
Yeah,
Or
here you
properties.
only work with the total parameters. So
Okay.
yeah. So can I erase this?
Yes.
So once you have solved that for TT2, once you have TT2, you can write that. I'm trying to find the best way to do that simply. So you solve that for TT2. Then to find M2, you want to know TT2 over T star. TT star, sorry. Because this is in the tables. And this is related to M2. So if you know this ratio, you will know M2. So you don't know TT star, but you can decompose this ratio like that. TT2 over TT star equals TT2 over TT1 times TD1 over TT star. Okay.
Okay.
And since you have solved that for TT2, you have this first one, TT1, and you have both, TT1 and TT2.
And the other one's a function of the Mach.
Exactly. And this one comes from the tables at M1 equals 0.5.
Okay.
So once you have TT2 over TT star, you look at the Rayleigh flow tables here. You have TT over TT star, and you look to the closest one to this to get M2.
Okay.
Which would be higher than this one, because when you heat, you accelerate.
Okay. And that's all the theory for Rayleigh.
That's pretty much it. Same for PT2 over PT star, same.
Okay.
Here. Same principle.
Awesome. Okay. Now I know a little bit of theory.
Yeah.
Thank you.